Hey guys, this video is about equilibrium calculations. And we're going to start out with an example. We're told that carbon monoxide reacts with steam, which is just gaseous water, to produce carbon dioxide and hydrogen, all gases. The equilibrium constant we're given, 5.10 at 700 Kelvin, and we're asked to calculate the equilibrium concentrations of everything present, all species present, if we start out with 0.23 moles of carbon monoxide and 0.55 more moles of steam, water, in a 125 milliliter flask at 700 Kelvin. And so basically the approach is to write down the equilibrium expression using x, well, whatever variable you want, but I usually use x to represent how much of each species shifts as it comes to equilibrium, and then solve the equilibrium expression for x, which will allow us to calculate the equilibrium concentrations. Why don't you guys go ahead and give that a shot, and when you finish, come on back. Welcome back, guys. So first of all, we need a balanced equation. And we're told what the reactants and products are: carbon monoxide and steam making carbon dioxide and hydrogen gas. All gases balanced, all coefficients of 1, there's our K. First of all, because we start out with only carbon monoxide and steam in that flask, the initial concentrations of carbon dioxide and hydrogen are both 0. That means that Q is equal to 0 also, and that's definitely less than K. Because Q is less than K, we know the equilibrium will shift to the right in order to achieve equilibrium. And that's going to be important here. So what we're going to do is we're going to start out calculating the initial concentrations of everything present before the reaction even starts, right? So just as we put them in there. And so we take the moles divided by the liters, get the molarity of carbon monoxide and steam, water. The initial concentrations of carbon dioxide and hydrogen are both 0. And then here's that X I was talking about. So we start out with some carbon monoxide and steam, no carbon dioxide and hydrogen. We know the equilibrium is going to shift this way, to the right. That means we're going to lose some carbon monoxide and some steam. And if we call that amount X, it's going to be the same amount because each of these has a coefficient of 1. So for every 1 mole of carbon monoxide that we lose, we also lose 1 mole of water, steam. And because these coefficients are also 1, we gain 1 mole of carbon dioxide for every 1 mole of each of these we lose, and we gain 1 mole of hydrogen. So that amount that we lose and gain, we're going to call X. So the change for carbon monoxide will be minus X. For steam, it'll be minus X. For carbon dioxide, it'll be plus X because we're gaining that. And for hydrogen, it'll be plus X because we're gaining that too. And so that means at equilibrium, the concentration of carbon monoxide is going to be the initial concentration minus X. Concentration of steam will be its initial concentration minus X. The concentration of carbon dioxide will just be X, or 0 plus X if you will. Same thing for hydrogen. So that's enough information right here to write down the equilibrium expression. So K is equal to products, so for reactants, East raised to the powers of their coefficients. So concentration of carbon dioxide is X, concentration of hydrogen is X, X times X is X squared, that's where that comes from. Concentration of carbon monoxide at equilibrium is 1.872 minus X, and steam is this. So this, guys, is a quadratic, second order polynomial. And so we solve that. So a word on solving quadratics. As we do the homework, the worksheets and these problems right here, and the quizzes, it's up to you how you solve that. If you really want to do, solve a quadratic formula by hand, that's fine. Most calculators, though, have a solver on them, and it's probably worth your while to learn how to use it. That's what I did here. I just plugged this into my calculator, and it gave me 2 roots. Now, real quick, a word on exams, because that's a whole different story. You will not have to solve a quadratic or higher equation during the exam. I'll show you an approximation later on in this video that you will always be able to make whenever you get to this point on an exam. because it's just not fair if one person has a better calculator than another that they could solve this faster. So you won't have, that's not going to be an issue on exams. But I definitely want you to learn how to do this. All right, so solving this equation, I get two roots. Now, okay, second order, so there's going to be two roots, right? Now, one of the roots, we can use our chemical knowledge to throw it as nonsense, because if x is 6.16, that means we get at equilibrium we would have negative concentrations for both carbon monoxide and steam. And that's nonsense. That's nonsense. It makes no sense chemically whatsoever. So we can just throw that root out. The one that's left does make sense, and that will be our answer. So now that we know x, we were asked to find the equilibrium concentrations of all the species. So what we do is we use x back up here at our equilibrium concentrations. So at equilibrium, the concentration of carbon monoxide rather, will be 1.872 minus 1.673. This is our x right here, right there. And 0.20 molar. Steam, 4.432 minus x again, which is 2.76 molar. Concentration of carbon dioxide and hydrogen, because there was none initially and their coefficients are both 1, they'll just be x, which is 1.67 molar. Now, when we're doing a problem like this, I don't know if it's a shortcut, but it sure makes things a lot easier and it cleans things up so nicely. It's called an ice table. And so this is how we're going to do almost all of our equilibrium problems, equilibrium calculations with ice tables. ICE stands for initial, change, and equilibrium concentrations. So what you do, we already did all this, but it was so much messier over there. Now if we set this up in a table, it looks so much cleaner, and there's less chance you're going to get confused as you go through. So what we do is, underneath carbon monoxide, we calculate its initial concentration. We did that previously. Same thing for steam, and the initial concentrations in this example are 0 for both of the products. Our change was minus x plus x plus x. So at equilibrium, we have the equilibrium concentrations involving x. Now all we have to do is plug these values into the equilibrium expression. Products, x squared, it ends up, over reactants. And we get the same thing, solve it, and we get the answer, x. All right, so another example. 1.293 grams of water, 2.090 grams of dichlorine monoxide, and 2.419 grams of hypochlorous acid are placed in a 1.750 liter flask at 25 Celsius. So that's giving you enough information to calculate the initial concentrations, right? So I'm thinking ice table already, right? Given the mass, that means we can get the moles, and divide by the volume gets us the liters. You're given the balanced equation here, right? And you're given K. So basically, same idea, set up the ice table, set up the equilibrium expression, solve for x, use it to find the equilibrium concentrations. Why don't you guys go ahead and work that out, and come on back when you get an answer. Welcome back, guys. So first thing we have to do, we have to figure out which way this equilibrium is going to shift, because in this problem we start with some of everything, some reactants and some product. So calculate the initial concentrations, use those to calculate Q. So the initial concentration of water, just the mass over the molar mass divided by the volume. Same idea for dichlorine monoxide and hypochlorous acid. So we get these concentrations. Plugging into Q, remember Q is just like K, except it's not necessarily at equilibrium. What we do, when we plug these numbers in, check my work, make sure you guys do this, I get a value of about 1.232 for Q. K is 0.09, so Q is greater than K. That means there's too many products, not enough reactants. It's going to shift to the left, to the reactant side. And that's going to be really important. Without knowing that information, we would be guessing, which is never good when we set up our ice table. So remember, we've just figured out now that the equilibrium will shift to the left. All right, so setting up our ice table, there's our initial concentrations. Now here's where knowing which way the equilibrium shifts come in. because we know, and the only way we know this, guys, is because we calculated Q and compared it to K. It was bigger than K, Q was bigger than K. So that tells us we know the equilibrium is going to shift to the left, which means we're going to gain some steam and some dichlorine monoxide. So that's why it's plus X, not minus X here. And we're going to lose some hypochlorous acid. So it's minus 2X, 2 because of this 2 right here, right? For every 1 mole of steam that we make, we lose 2 moles of hypochlorous acid. So minus 2X. And now we get an expression for each of the equilibrium concentrations for all the species. Just plug them into the equilibrium expression, right? See, starting to get the idea. It's all pretty much the same. Here we're going to use got to remember the squared here too. That's pretty common. People forget the squared up there. Anyway, plug in here. Once more, we get a quadratic formula. Solve it. Get 2 roots. We can neglect this root. We can throw this root out, because if x is basically 0.02, that means 2x is basically 0.04, and we get a negative concentration for hypochlorous acid, which again is nonsense. Right? So we throw out this root, and that's always going to happen, guys. When you get 2 roots, you're always going to be able to discard 1 using your chemical knowledge. This root does make sense, so that means now we know the equilibrium concentrations of everything. Equilibrium concentration of water, we add X to the initial concentration. Dichlorine monoxide, we add X to the initial concentration. And hypochlorous acid, we subtract 2X. Watch out for that 2, guys, and to get the equilibrium concentration. And there's our answers. Now, this is a good habit. You guys should get into this habit. You can check your work really easily, and a lot of times if you made a mistake, you'll catch it this way by just plugging the values that you calculated, so these values down here, into the equilibrium expression, and making sure you get pretty close to the same value of K that you were originally given. So when we plug in these values that we got for all the species present, we get 0.08999, which rounds to 0.0900, which is the same. So now we can be even more confident in our answer. Just takes a few, less than a minute probably, and once you get the hang of this stuff, and it's a really good check. So I really recommend you do that. All right. Another example. We're given a reaction down here. And we're given the equilibrium concentration. So now, instead of being the initial concentrations, we know how much of everything there is at equilibrium. We want to calculate what happens is, so we start out with this stuff in there. This is how much of everything we have. It's at equilibrium. And then we add 0.0314 moles of fluorine gas, this stuff right here, to the flask. So now it's not at equilibrium anymore, right? So it's going to shift, and we want to find the new concentrations at equilibrium. So a couple things, we know we don't even have to calculate Q, because we have more of one of the reactants than we did at equilibrium, which means that Q is going to be less than K, and equilibrium is going to shift to the right. And that's going to be important. So why don't you guys go ahead and work on this, and come on back when you get an answer. Welcome back, guys. So, like I said, we already know that it's going to shift to the right. So what we use those equilibrium concentrations for is to calculate the value of K. Right? That's one of the things we use them for. So if we plug all the equilibrium concentrations into the equilibrium expression, products over the reactants, raised to the powers of their coefficients, we get K, about 3.17. And we'll use that in the calculations later on. Now we get to set up the ice table. So we added 0.0314 moles of fluorine, and the volume was 750 mils, or 0.750 liters. That means we added 0.04186 moles per liter of fluorine. So that means that the initial fluorine concentration for our new equilibrium is going to be its initial molarity plus what we added, or 0.1488 molar. So that lets us set up our ice table. So initially we had 0.493 moles per liter of hydrogen. Now we have 0.1488 moles per liter of fluorine, and 0.409 moles per liter of hydrogen fluoride, or hydrofluoric acid. And because we know the equilibrium is going to shift to the right, again, we know that because we added a reactant. So we made this number down here too big, which made K too small, or Q too small. So Q is less than K, so it shifts to the right. Which means that if to shift to the right, we're going to lose some hydrogen and fluorine. That's why it's minus X here and minus X here and plus 2X here, because we make 2 hydrogen fluorides for every one of each of these that we lose. And so at equilibrium, we get our concentrations in terms of X. We can plug into the equilibrium expression. So there's hydrogen fluoride, 0.409 plus 2X, whole thing squared, and then hydrogen, fluorine, both minus X. Get a quadratic equation, 2 roots. One of the roots makes no sense, negative makes no sense, and it's also too big. Because when we subtract it, we get some weird number. Anyway, one of the roots makes sense, and that's our answer. So now to get the equilibrium concentrations, we just plug in X to these expressions here. So we get 0.475 moles per liter for hydrogen, 0.131 moles per liter for fluorine, and 0.445 moles per liter for hydrogen fluoride. So checking against K, so plugging into the equilibrium expression, put these numbers in and we get 3.17. All right, so now we can be even more confident that we got a good answer. So a lot of the times, okay, so we're going to deal with equilibria that have small k's. And this is what I was referring to earlier. This is where we can solve it without having to actually solve a quadratic or even a cubic or quartic, what have you. So the idea is that when the value of k is small, we can make these approximations that make the algebra actually a lot simpler. We'll call that neglecting x. That's what I mean when I say you can neglect x, what I'm about to show you. So we'll use an example. So we start out with a flask where we put some carbon dioxide in here. Here's the equilibrium down here. There's its initial concentration, some carbon monoxide, that's its initial concentration. No oxygen, 0. So right away, before we even go any farther, because the concentration of one of the products is 0, that means Q is 0, Q is less than K, equilibrium will shift to the right. Again, that's important to know so that we know if we do plus X or minus X in our ice table. So we want to find the initial equilibrium concentrations of oxygen, O2, at equilibrium. And temperature stays constant at 25 Celsius, so that means K's. We can use this K. So guys, why don't you go ahead and work this out and come on back when you get an answer, okay? Welcome back, guys. All right, so let's work this out. So there's our equilibrium, there's our K, this is our ice table, initial concentration, initial concentration, initial concentration. So because it's going to shift to the right, we're going to gain some carbon monoxide, that's why it's 2X here. X here, we're going to lose some carbon dioxide, that's why it's minus 2X here. So these are the equilibrium concentrations in terms of X. Plugging into the equilibrium expression, products over reactants, so this is carbon monoxide, this is oxygen, and this is carbon dioxide. Again, notice the squares here. So this is a cubic equation, which has some really cool behavior, but it's really pretty tedious to solve by hand. And now, if you have a calculator with a solver on it, it'll do it for you, but we're not going to worry about that because we're going to neglect X. Because look down here, right? This is a pretty small K. 2.04 times 10 to the minus 6, 0.0000204, right? And so small k means that we don't make very much products. So let's say, there's our equilibrium expression, so if we don't make much products, that means x is going to be pretty small. So why don't we say, what if 2x is less than 0.109? That means we can neglect it here. And if 2x is a lot less than 0.109, it's also going to be less than 0.143 because 0.143 is bigger than 0.109. So neglecting 2x here, we can't neglect x here because we're not adding or subtracting it to anything. We're multiplying, so then we definitely can't leave this x out. It has to be there. So we get this is neglecting the 2x here. So now it's not even a quadratic anymore. All we have to do is rearrange this and we get x, right? Multiply through by 0.109 squared, divide by 0.143 squared, and I get x is 1.18525 times 10 to the minus 6 more. That's definitely, our assumption was definitely a good assumption, because 1.18 times 10 to the minus 6 is certainly a lot less than, or 2 times that anyway, is a lot less than 0.109. Now, I went ahead and I solved the full cubic equation just to show you guys. And when I did, we got 3 roots, of course. 2 of them were imaginary, so imaginary roots don't make sense in this context, so we ignore those. The one real root is the one that makes sense, and the only difference is buried in the insignificant figures. That's why I put the first 3 insignificant figures. I usually just put the first one. So 525 were the first 3 insignificant figures with the assumption. 516, the first 3 without the assumption. So it's, for all purposes, it's the same. And so we were asked to find the equilibrium concentration of oxygen, which we can see is just equal to x. So there it is, 1.18 times 10 to the minus 6 molar. All right, so a couple of things. We can play with this idea a little bit. If you start with an equilibrium with a fairly large K, right, a couple hundred, maybe a couple thousand, or even bigger, then what we can do is we can use this same idea, but here's what we do. Is we start out, with what we're given, and then assume that it goes to completion, because a large K essentially means the reaction goes to completion. And then we flip it around. And now, because remember, when we reverse the equilibrium, we take 1 over K. So now the K becomes really small. If K in the forward direction is really large, K in the reverse direction will be really small. Our initial concentrations will be what we got from the reaction basically going to completion, the stoichiometry stuff that we did last semester in Chem 101. Now we can use this assumption, right? So this is actually a really useful assumption. We can do it a lot of the time. Here's something that you guys should do. Go back and look at those examples we worked out earlier in this video and see if we could have neglected x. Okay. So how do we know? Well, in the example we just did, it was pretty obvious that 1.18 times 10 to the minus 6 times 2 is a lot less than 0.109, right? And it's less, it's in the insignificant figure somewhere, right? But that's not always the case. So we have a rule of thumb, and it's just that, just a rule of thumb. It's not a hard and bright line. But what we're going to say is if the value that we neglected, which was 2x in the previous example, is 5% or less compared to the number we neglected it relative to. So if 2x is less than 5% of 0.109 in that last example, then we'll say, okay, that's a valid approximation, and any difference that we get from our approximation will not really matter. However, if the value we get is much larger than 5% of the value we neglected it relative to, then we know that assumption wasn't good, and we're gonna have to go back and solve the full equation. And that's all there is to that, guys.